Okay, so today in class we did some reviewing on energy, which you will take a quiz slash test on the next class we have. So we went through a few examples of energy bar charts. I guess maybe just a couple, maybe three. I don't remember. Um, Examples of energy bar chart things, and then we talked about the 6 forms of energy. So this was the first scenario. The before shot was a person on top of a roof or something, I don't know. And then they go down here onto a trampoline, and then there's an after. So, what I would do if I were you, I would pause the video and see what you think there is before and after in terms of energy um, for the initial and the final, or the before and the after, and then start playing the video again, and then you can see what I was thinking in terms of what this should look like, possibly. So again, sketch the little deal here, try to figure out, and then tune back in. And I'll just go right through it right now. So I'm assuming that if you haven't done it yet, you're pausing the video right now. I hope you're pausing the video right now to work on this yourself, because the only way to get better at something is to practice it. Watching me do it isn't practicing. So hopefully you've done that. For the before, the initial picture, and notice I have a little 0 mark here, which is about at the bottom of where the trampoline is going to end up going. I just noticed I need some more. Oh no. I don't even know what color my pen is right now. But anyway, I'm going to say that this person, that this person has a full 4 blocks, of gravitational energy as he or she stands up here at the top of the building or whatever that is. Now, for the after, I'm going to assume that the person is not still moving, that this is at the maximum stretch of the trampoline and springs. And so I'm going to assume then that we have no height, we have no motion at this point. So it seems to me that that would mean that all of the energy that we had that was gravitational has now become elastic. Now, maybe you're thinking that some of that should be E internal, that maybe not all of this gravitational energy got stored as elastic. Okay, that's fine too. If you want, maybe there's a half a block here of E internal, and then the rest of it is elastic. That's fine too. Again, and I've said this before, I usually don't use E internal unless there is an obvious loss of mechanical energy in the scenario. That's just me. I'm just making it easier on myself. All right, so next, let's see. I made this one. Oh no. Oh, pretend you did not see that. Oh gosh. Well, I guess it's too late now. It's too late now. Now I'm totally in the way. I need to make myself smaller. Okay, so apparently you don't get to try this one on your own. I did not erase it already. So as we see here, we have a little roller coaster, okay, a little person inside. We have hill A, and then B, and then C. What we said at the beginning, and what I said in class, was that at position A, there is no movement. The car of the roller coaster just barely made it up there and is just kind of teetering on the top of the hill, and is going to eventually just make it over the edge, just barely make it over the edge. So I would say that all of the energy of the roller coaster car, excuse me, oh my gosh, whew, that all of the energy is gravitational due to the height. Then at the hill at position B, it looks like about half of the height is still there. Oh, also notice, in these energy bar charts, it's not just a before and after. I have multiple locations here. And I did not include E internal on any of it. So there's not even a question now as to whether or not all of the mechanical energy is still mechanical or has it been internalized into the jostling of the particles. No question. All of it is still mechanical the whole time. So at the hill B here, it looks like it's about half as tall as the original hill. Half as tall means only half of the gravitational energy is still there. Again, if I said 4 blocks at the beginning, only half of that is still there. The other half is now kinetic because it's probably moving pretty good right here. Now, I don't have any lines of motion here because I wanted you to actually think about it yourself. And then here we have another hill that looks to be about half as tall as this one, or about a fourth as tall as this one, which means the gravitational is even less now. But that means that it must be faster. So if it's not even moving at the top of this hill, then it's probably moving pretty good here. And then by the time you get to the third hill here, it's moving pretty fast because most of the energy that it had gravitationally at the beginning is kinetic now because only a tiny bit is gravitational. Hopefully that makes sense. Now the question is, did I erase this one? Okay, so I did clear that one. Jeesh. So here's another one. Okay, here's another one. Take a look. Sketch it out. Pause the video. Pause the video so you can sketch it all out. Do it, and then come back. I'm assuming you paused it and went and did it, and now you're back because I'm going to start talking about it. It looks like at the beginning we have nothing. Nothing. There's no EK. The box is sitting on the ground. There's no EG. There's nothing that's been stored elastically. Nothing. At the end, the box is now at the top of the staircase and even being held up above the floor. So I'm going to say that is a lot of gravitational. I'm going to say 4 blocks worth because I can. So 4 blocks worth of EG. Here's the problem. We have nothing on the left. We have 4 blocks of energy on the right. And we know, due to the law of conservation of energy, that that can't be. So how do we explain that? Well, there is a person in the video in the picture, who seems a little sad, actually. And this person appears to have carried this, well, first lifted it and then carried it up the steps. That means the person did some what? Did some work. How much work? Well, the work done is exactly the amount equal to how much gravitational energy the object now has. We couldn't get something for nothing. So that means work had to have been done to the block, box, whatever it is. That means energy was transferred to it by the person. How much? Well, I would say 1, 2, 3, 4. Work. Oops, that's an odd. So work was done into the system by the person in the amount that is how much energy the object gained, transferred energy through motion. Got that? I hope you got that. Now, the last thing we did is we talked about the 6 forms of energy, which you already have in your notes. But I don't know if you wrote these things down. We had talked about these things, but I didn't know if you wrote them down. So I'm just going to briefly go down through and mention some things about these. Thermal. When we talk about thermal energy, what is that associated with? It's associated with the actual movement of the particles, okay? The particles in matter are moving, shaking, and vibrating all the time. The faster they move, shake, and vibrate, the more energy that substance has thermally. Now, that sounds like a kinetic thing. So that is definitely an energy of motion thing, thermal. Mechanical. So when we're talking about mechanical, we're talking about all the stuff that we've been talking about in terms of kinetic. Anytime something's moving, we have kinetic, which again, that could be moving parts of a machine of some kind, the parts of a car and the motor and the transmission. That's all mechanical, kinetic movement. Sound would be a kinetic or movement thing. Then, of course, we have gravitational and we have elastic. And again, we have stored. So energy can be stored elastically and gravitationally, or we can have motion involved, which would be EK. So we have both stored and motion energy. Radiant. Radiant has to do with radiation or electromagnetic waves. Things like, again, infrared, ultraviolet, radio, micro, X, gamma. Those are all different kinds of electromagnetic waves and radiation. They are energy. It is an energy wave, and they move. So it's kind of a kinetic thing. In fact, they travel very fast. The speed of light. Oh, let's see. Nuclear. The energy with nuclear resides in the mass of the nucleus itself. The matter and the particles that are in the nucleus, they have and possess energy. They are energy. And that energy can be released during things like fission and fusion, okay? Fission and fusion, or nuclear decay, which is, it is fission. It's splitting apart. The nucleus falls apart. And when the nucleus falls apart and particles fall out of the nucleus, that is nuclear decay, we would call it. So sometimes with fission, we think that is a forced splitting of an atom's nucleus. Decay kind of happens on its own. So it's kind of how we normally think of it. That is stored, I would say, stored energy, because it is in the nucleus, in the mass of the nucleus. And so some special event has to happen for that energy to come out. Electrical. We're talking about electrons that are flowing through a conductor, typically, is what we're referring to with electrical energy. And that, since it says electrons flowing through, that seems like it's mostly a kinetic or movement kind of energy. And then we have chemical. And again, the energy with chemical energy is stored in the chemical bonds, which are forces. Those are the forces that are holding the atoms and molecules together in a substance. So chemical energy, again, is stored in the bonds or the forces that are holding the matter together. So that right there, those are the 6 forms of energy. You need to be familiar with them. I will ask you some questions about those 6 forms of energy. Let's see. I would know those. I would be very familiar with the energy bar charts and how to construct those. I'll just ask you a bunch of questions about energy and the ways we see and experience it. Mostly about mechanical, but also about these 6 forms. I will not ask you what the 6 forms are, I don't believe. I just want to know, do you understand how energy can be found in these different ways. Like for instance, if I burn a log, like I have a campfire and a log is burning. First of all, what kind of energy do you think the log has just itself? I hope you're thinking chemical energy, because the log just sitting there, it doesn't appear to have anything, because the energy that it has is stored chemically in the bonds that hold the stuff together. And because a log or paper or any kind of organic material like that can be burned, or even if it's a fossil fuel like coal, oil, gasoline, kerosene, any of those kinds of fuels that can be burned, natural gas, propane, they have chemical energy in the chemical bonds that hold that stuff together. And so chemical energy in the log becomes what in the campfire? The chemical energy found in the log becomes thermal, because campfires give off heat, and radiant, because typically campfires give off some light. Could be the flame itself, could be the glowing embers, the coals that are there, a lot of radiant energy being given off by that, a lot of infrared for sure, and visible light. So questions like that about how do you get maybe sometimes from one to the other. Like if I rub my hands together on a cold day, the friction forces are allowing me to take what kind of energy and produce what. I'm able to go from what form to what form because of the friction forces between my hand. Again, the moving of my hands back and forth is a what? That is a mechanical energy. And that allows me to produce what? A thermal energy because of the friction forces between my hands. So again, a lot of questions like those. In terms of the 6 forms, I might ask you about that. If you can identify what form of energy certain events or certain circumstances has. So hopefully you actually do some studying and prepare, and that'll be, I think, about it. If you do have any questions, be sure to let me know. Otherwise, we will see you later. Take care.